Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hi, everyone. Good day. Welcome to the 9th session of the AI for Good Discovery Series on AI for Biodiversity. This series represents a partnership between the International Telecommunications Union, the Convention on Biological Diversity, NatureServe, and the Alexander von Humboldt Institute of Columbia. And my name is Mike Gill, and I'm the director of the Biodiversity Indicators Program at NatureServe. And NatureServe is a science-based organization operating a North American-wide network for the conservation of at-risk species and ecosystems. Now, the intent of this series is really to explore the intersections between AI and biodiversity knowledge and conservation, delving into the ways that AI is transforming this space, but also discussing the challenges and bottlenecks that we may be facing in terms of fully realizing the opportunities that AI can represent. And of course, AI is just one toolbox in a conservationist toolkit, but one that's really accelerating in leaps and bounds, not just at the programming level, but also in the creative ways that many scientists and others are applying it to solve problems. So in this 9th session called Unlocking the Symphony of Birds, we'll hear about the Merlin Sound ID, which is a cutting-edge machine learning system that brings the magic of bird identification to life on your mobile device in real time. And with a simple tap, your phone's microphone becomes a gateway to the symphony of nature's voices as Sound ID reveals the hidden identities of avian artists in your surroundings. Now, I am a big user and a big fan of Merlin Sound ID myself, and also a user of where that data goes, the eBird data, in my own research. And I can definitely attest from personal experience how this application is incredibly powerful, both in connecting people to nature. So people in my community, I talk about this app all the time. Everyone downloads it and uses it. To better understand nature in their backyards, but also it's really leveraging our ability to continue to build on an already impressive eBird database. And so I'm very much looking forward to having a front row seat to view the under the hood, so the underpinnings, applications, and future plans for this particular application. So with that, let me introduce my two speakers. So first, we'll have Grant Van Horn, whose research lies at the intersection of computer vision and machine learning, and focusing on creating intelligent information systems that blend human expertise, advanced machine learning techniques, and large data sets. His work is driven by a commitment to leveraging these technologies for public engagement and supporting scientific endeavors in biodiversity and conservation. Notably, his contributions power popular wildlife identification applications such as iNaturalist, Seek, and of course the Merlin Bird ID. After finishing his doctoral studies at Caltech, Grant spent 6 months as a researcher at AWS before joining Cornell and working with the Cornell Lab of Ornithology as a researcher for 4 years. In the fall of 2023, he joined the College of Information and Computer Sciences at UMass, University of Massachusetts, Amherst, as an assistant professor. Grant's undergraduate work was recognized with the Computing Research Association Outstanding Undergraduate Researcher Honorable Mention Award. His PhD work was recognized with the Ben P.C. Chow Doctoral Prize in Information Science and Technology from Caltech. We also will have, after Grant, a second speaker, which is Dr. Eliot Miller, who is a researcher at the Cornell Lab of Ornithology and is currently working as a Smith Futures Fellow. The focus of his current project is incorporating detections from automated acoustic ID into species distribution models, and his research focuses on understanding why species occur where they do and why they look how they do, with an increasing interest in what this information can teach us about forestalling our ongoing biodiversity crisis, using phylogenetic comparative methods and the synthesis of field, museum, and citizen science data on the behavioral, ecological, and morphological attributes of organisms. He's striving to address fundamental questions of biodiversity. So with that, welcome to both of you. Thanks so much for doing this, and I'll pass it over to Grant to start the presentation.
Awesome. Thanks, Mike, for the intro. Let me just share my screen. All right. So like Mike mentioned, Eliot and I will be talking about Merlin Sound ID. And we'll kick it off with trying to kind of share our inspiration for building this thing. So if you can take a second to imagine you are walking down this path, this is just outside the Lab of Ornithology building in upstate New York, and you're hearing a bunch of bird noises. And let's take a listen. Now these bird noises are beautiful, and it really improves your experience kind of walking down that trail, listening to these things. But unless you're a birder for a long time, or you have an ornithologist friend, it's often really difficult to know what is actually making those noises, right? What species are you sharing that trail with? And what is their life history story, and how do they connect to the broader environment? And our inspiration for building Merlin Sound ID was to try to put the expertise of ornithologists that can do birding by ear into your pocket, because most of us have a cell phone these days with a microphone. And wouldn't it be cool if you could take out that phone, turn on your microphone, and have the app kind of tell you what is singing? So in this talk, I'll kind of open up that process into how we built Merlin Sound ID. And Eliot will then, toward the end, Eliot will take over, and he will describe kind of what the future holds for this project. What kind of cool science is this unlocking? And and what's in store. So I get, or the folks on this project get lots of questions, and these are things like, how did we build Sound ID? Why doesn't Sound ID cover all the bird species? How well does Sound ID perform? And how do you improve Sound ID? I found a mistake. Like, how do you make it better? So my goal for this talk is to kind of touch on all of these questions, at a relatively high level. But yeah, hopefully, over the course of the next 30 minutes or so, you should, you kind of get to see kind of all these pieces, and we should hopefully answer most of those questions. So the first thing to note is that Sound ID is not like a linear process. We started it 3 years ago, and there's not necessarily like an end in sight. It's this iterative loop, so to speak, that we kind of keep going through to add species, to improve performance, to kind of take feedback from the community. But this loop kind of involves four main pieces, right? One is collecting audio. We need examples of what birds sound like in order to kind of teach the system. So the collection step here is a major piece, followed by an annotation process, right? And that's to annotate the actual vocalizations in those audio files. Once we kind of have those two pieces in place, we can then teach Merlin how to detect and classify these bird vocalizations. But you don't want to just take Merlin at its word. You want to test it. You want to sort of really investigate whether it has actually learned what these birds sound like before we kind of release these models to the public. And we'll then take kind of our lessons learned in that testing phase, that step 4, and repeat this process, right? We'll just keep looping through this thing. And the project's been running for 3 years, and we've done sort of countless iterations of this cycle. We try to do like one of these cycles every week, actually, touch on all 4 steps. But let's dive into each one. So we start with the audio collection phase. And all of the audio that kind of powers this app is coming from citizen scientists that are outside observing birds, right? And this could be like in our backyard, sort of in the northeast of the United States, collecting data on the species that occur on our front step, or it could be in more remote locations. It could be, these photos show a recent expedition that Cornell put together to put some undergrad researchers out in the field in the Amazon to collect more audio recordings of bird species that we just don't have much audio for. But kind of regardless of who's doing the collection, these scientists contribute their data through a platform called eBird. And Mike mentioned eBird in the introduction, but it's a massive citizen science operation that allows folks to go to a particular place at a particular time and tell us what bird species they saw. So yeah, this is a screenshot of the web interface for eBird. In this case, John saw 22 species, and he contributed audio or media for those observations. So for this pin-tailed sand grouse, John contributed 2 audio recordings, and for the Iberian gray shrike, he contributed 2 more audio recordings. Now, these audio recordings here are actually, what you're seeing here is a spectrogram, and you're going to see these figures, these like kind of icons all over this presentation. And what I need you to do is, like, every time you kind of see these gray and white images with squiggles, is just think of audio. This is an MP3 file, or whatever you want to think of when it comes to audio. But these images here represent an audio file that the citizen scientists contributed. So we have eBirders out in the field collecting audio and uploading them, and those audio files get archived at the Macaulay Library in the Cornell Lab of Ornithology. And so this is a large repository of both audio, video, and photographs. For this talk, I'll mainly be talking about the audio portion of it. But again, it's a place where anybody can go to. So anyone can go to macaulaylibrary.org and kind of browse all of the audio files that we've collected. In this case, we're looking at a particular asset. Again, we'll tell you kind of who was the recordist, when did they do the recording, and where were they, along with what the kind of the target species of that audio file is. And the Macaulay Library has been aggregating audio for a long time. So some of the earliest recordings are from the 1920s. Those are like some of the first recordings ever of bird vocalizations, and it's been continuing. So what you're seeing here is a black square where we render latitude, longitude coordinates of where we've received audio files. And you've seen, if you notice in like kind of the last few years, the map really started popping, right? And that's because we've seen this big growth in audio contributions, mainly because of the partnership between the Macaulay Library and eBird that opened up in about 2017. So what this plot is showing you is sort of the cumulative number of audio files that the Macaulay Library archives. We've surpassed 1 million natural sounds, and then along with the monthly contributions. And so you see these spikes, and those spikes correlate to springtime in the northern hemisphere, right? So birds in the northern hemisphere, birds are quite vocal. And so we get a lot of recordists outside kind of contributing audio from the northern hemisphere during those times of the year, but we're seeing this kind of overall growth as well across all the months. The challenge here is that the audio that's the citizen scientists are contributing are not uniformly distributed across species, right? So this plot shows species sorted in descending order of audio files. So the species, there's about 10,000 bird species in the world. In the Macaulay Library, the species with the most assets, over 10,000, is the red crossbill. And we have 231 species that have over 1,000 audio files, and about 1,700 species that have over 100 audio files. And that leaves, about 8,000 or so odd species that have less than 100, and many actually that have less than 10 audio files. So to answer one of those questions from the very beginning of the presentation about why doesn't Sound ID just cover all the bird species in the world? Well, the Macaulay Library doesn't quite have enough data, enough audio recordings for all the species in the world. So for the Sound ID project, we focus mainly on species that have at least 100 audio files. And at this time, that's only about 1,700 birds. Now, the Macaulay Library is constantly growing. We'll get another, probably 1,000 audio recordings today. And, maybe that will bump up a few more species to have over 100 audio files. And that's why this project is iterative. We get more data, and as species kind of pass this threshold, we can start working on them to bring them into Sound ID. But let's assume that we kind of focus on one of these birds that does have enough audio files. How do we onboard it? How do we get it into the project? Well, we start by looking at the distribution of its audio files on a map, right? So these are all of our audio files for the yellow-rumped warbler. And we can see its distribution kind of spans the United States and up into Canada and Alaska and down into Central America. And this particular species has 3,000 audio recordings, right? So this has sort of an excess of audio. And you'll see later on in this presentation that we don't necessarily want to be working with all of that audio. There's probably a lot of redundancy, and we don't need to push it through some of our annotation pipelines because we'd be wasting time. So what we want to do is we want to kind of group the audio files together based off of location and date. And that's what this kind of clustering visualization shows. So what we've done here is we've grouped the files based off of kind of where they were recorded and when they were recorded, right? So this is kind of a busy plot, but if we just isolate one of these clusters, this is kind of our West Coast winter group. So all of the audio files visualized by these dots were taken in the first 2 weeks of January, kind of in the western part of the United States. Meanwhile, we have a Northeast spring group, right? So these are all audio files that were taken sort of in the Northeast of the United States and into Canada in the last 2 weeks of May, for example, right? And the reason we group these audio files together is that we expect kind of vocalizations and possibly even habitat noises to sound relatively similar in these files. And so we can just subsample a few recordings from each cluster. Now that subsampling, that selecting of audio is going to produce two what we call splits. One is a train split and one is a test split. So all the yellow dots here are going to represent audio recordings that we're going to use to teach Merlin what the yellow-rumped warbler sounds like. And the test files are audio that we're going to use to quiz Merlin. It's basically an exam so that we can see, did it actually learn what a yellow-rumped warbler looks like? And it's kind of this like train test split thing is actually kind of nice to think about as like a homework and exam setting, right? So all of these training files, again, we're looking at our spectrograms of the audio. All of those training files are things that Merlin can take home, so to speak, and learn, used as resources to learn what a yellow-rumped warbler sounds like. And then the test files are things that we're going to hold out. Merlin never gets to see these, and we're just going to use them to quiz every once in a while to see, like, okay, Merlin, did you really learn what a yellow-rumped warbler sounds like? These train test splits are really important. They underpin a lot of our machine learning and AI work. And you'll see them kind of come out later in this presentation as well. But that's kind of our audio pipeline, right? So we have audio coming in from eBird into the Macaulay Library. We can then subsample a few of those audio files to actually onboard a species. But now we go into our annotate. We now go in and annotate the vocalizations. It's totally valid to ask, why bother annotating the vocalizations in these audio files, right? Like the scientists said that there was a yellow-rumped warbler in those audio files. Just tell Merlin that there's a yellow-rumped warbler in them. Well, let's kind of run with that idea for a second and just see kind of how easy it is to learn from the raw audio, so to speak, what a yellow rump warbler sounds like. So we're going to take a training file for the yellow rump warbler, and we're just going to listen to the first 20 seconds. And, it's kind of in your mind, just like if someone gave you that as a training example for yellow rump warbler, just see if it would be useful. So let's give a listen. Okay, so, there's a lot going on in that audio file. Are all of the noises that you heard, are all of those bird vocalizations? If they are, do they all belong to the yellow rump warbler? Do only a subset of the vocalizations belong to the yellow rump warbler? If so, which ones, right? This is really ambiguous. It's not impossible necessarily to learn from this data. This is like kind of a really exciting open research question in AI and machine learning. But like when you're just trying to build something, this is really ambiguous, really difficult data to work with. So what we do instead is we annotate the vocalizations in the audio file, right? So we're going to listen to that same 20 seconds of audio, but this time you will see the boxed vocalizations for the various birds that are vocalizing. So let's go ahead and give a listen. Okay, so, in this example, what we've done is we've like isolated each bird vocalization and we've labeled it with which species produced it, right? And so when you have that information, now it becomes very kind of clear, like, oh, okay, our yellow rump warbler are these sort of chip notes here that are being produced. And meanwhile, we have a Vesper sparrow kind of overlapping it. We have a northern cardinal vocalization going off. We have a red-winged blackbird as well. So this just makes the whole process of learning these bird vocalizations approachable. Like now it's like, okay, if you can imagine teaching a human with this kind of data, it becomes a bit easier to figure out, like, how do we teach a machine with this type of data? And so this is, so for every audio file that we sample to be part of the project, we try to get expert to come in and do this boxing. And that's why I was saying we don't want to bring in all 3,000 yellow rump warbler audio recordings. It's just a lot of data to go through, and it's probably redundant. So that's why we did that upfront kind of sampling to begin with. But even still, the process is quite detailed and it requires a lot of expertise to do. And so we've broken it down into regional projects. So the US and Canada was our first project, and we've since expanded from there. And we try to kind of engage with various experts in those regions to help do the annotations. And so in this GIF that you're seeing, we're watching an expert kind of annotate these vocalizations in our tool. So this is an elegant trogon recording that was taken in Arizona in the United States. And we're watching an expert kind of box the vocalizations and adding incidental species. So in this case, this is a brown-crested flycatcher that was vocalizing in the background. But like you saw in that yellow rump warbler, I mean, these files can get quite complicated. You can have many species kind of vocalizing on top of each other. You can have various background noises that makes it difficult to distinguish where a species vocalization starts and stops. And so, yeah, this is a big annotation project that, it's taken us 3 years to kind of get to this point where we've gotten 1,200 or so species ready to go. And again, this is kind of like why Sound ID doesn't work for everything immediately. This takes time to do this, and we onboard species in chunks. It seems like we do about 100 to 200 species with each new model release. And so, yeah, so just some kind of fun current annotation stats. The project's been running for 3 years. We've had 227 annotators come in and contribute their knowledge. They have drawn 2 million boxes on over 200,000 audio recordings. So the data set is becoming quite large. 3,721 bird species have at least one box, which is kind of cool. The species with the most boxes, we have the northern cardinal with almost 16,000 boxes, followed by house sparrow and red-winged blackbird. So these birds, especially in North American recordings, these species are just often in the background somewhere. So that's why they're getting all these boxes. And then these species are kind of our most recently encountered. So the swamp harrier got its first box vocalization just a few days ago. This came from a recording taken in New Zealand, and the white banded wren got its first box a few days ago as well, from an audio recording coming from the Amazon. Okay, so we have our audio collection pipelines and our annotation pipelines, and now we can combine those two things to build all the stuff we need to teach Merlin how to recognize sounds. And to kind of gain an appreciation for this, it's useful to remember what Merlin has to do on your phone, right? So when you're outside, birds are going to be producing vocalizations. That's propagated to you via sound waves, right? So it's a wave traveling in this case through air, and it's going to hit your microphone on your cell phone, and that microphone acts as a transducer, right? It has to convert mechanical energy, a sound wave, into an electrical energy. In this case, an electrical signal or an audio signal. And so this thing over here is what Merlin, the app, has to use to recognize bird vocalization. This is what we're going to get from the microphones. And this is sort of amplitude over time, and this is measured in decibels. And what we're going to do on the phones is take that audio signal and convert it into what we call a spectrogram. And we do that by passing it through or using an operation called the fast Fourier transform. And I'm not going to get into the details of that transform, but it's a relatively common operation that's used in a variety of applications. Your phone actually has like custom chips designed just to do this transformation very quickly and efficiently. But for acoustics, what it does is it takes this 1D signal and makes an image out of it, right? So these are those images that we've been seeing for spectrograms throughout this, for audio throughout this talk. And it's this that Merlin, the AI system, is going to be using to figure out what is vocalizing at any given time. And this should actually look very similar if you've ever opened up the Merlin app, because it's this same spectrogram that shows up here in the app. So this is a GIF of the app, and this spectrogram is that same thing that we just saw, right? So this is our audio signal that's been passed through the Fourier transform and then visualized. So, okay, so that's what Merlin needs to do, to work on your phones. So then how do we take our training examples and kind of replicate that process? Well, we're going to take, this is that same kind of yellow-rumped warbler audio file that we've been looking at. We're going to take this thing and we're going to chop it up into examples, right? And each example has its associated boxes. Those kind of get propagated down. And then we're going to train Merlin on each of these examples. And so this was a 6-second spectrogram, and it's been chopped up into 3 2-second spectrograms. So we're going to take each example. We're going to take the image representation without the boxes or anything, and show those to Merlin, right? So this is our kind of our cartoony version of the AI system for Merlin Sound ID. We're going to show it this spectrogram, and we're going to teach it to output ruby crowned kinglet and red-winged blackbird when it sees this image, right? So it's associating these species with these visual patterns. And we know that it needs to output these 2 species because those are the species that the experts boxed when they went and annotated the file. And meanwhile, it doesn't only have to say that these species are present, it has to say that every other species is absent, right? Like, this is a crucial piece. It has to say, it's not, it can't just say that everything is present, in which case it would get it right. It has to say, these 2 are present and all the other species that are under consideration are absent. And we're going to do the same process for all the examples. So here we have a yellow-rumped warbler vocalizing, a song sparrow, and a red-winged blackbird. We're going to take just the spectrogram, show it to our AI system, and get it to output just the species that are present, meanwhile saying that everything else is absent. And again, we continue on to the third example, same thing. And we're just going to repeat this process over and over and over, kind of until Merlin starts really figuring out which patterns in here correspond to the various species. Now, we don't just do this with 3 examples. We do this with many examples, right? So our most recent models that will be released to the public have 1,200 bird species in them. If you kind of concatenate all of those examples together, you would have 95 continuous days of audio, right? So if you sat down and you listened to it, you'd be listening to this audio for 95 days. Now, Merlin doesn't just look at an example once. It looks at it many times, right? Like you look at the same example several, if you're practicing bird vocalizations, you don't just listen to something once and then you have it down packed. You got to listen to it a few times and practice with it. And so if you take all, Merlin does the exact same thing. And if you took kind of all of that training data and added it up, it would be 39 years of cumulative listening for it to get to the point where we can release that model to the public. So these are kind of big operations. So, we parallelize these operations across a lot of machines. So while it's 39 years of cumulative listening, we can, the model training is actually only a few days. Okay, so now we can teach Merlin, and we can now move on to testing Merlin, right? And this is crucial, right? You kind of like it's never good practice to just trust a machine learning system, right? Like it could have learned random noise, it could have learned nothing at all. You really need to benchmark these things and see did they actually learn the concepts that you wanted them to learn. Okay, so the question that I get probably more often than anything else is how accurate is Sound ID? And I appreciate where the question is coming from, but it's phrased really in an odd way to me, right? This is a kind of like asking how accurate are you at listening? You can appreciate what the person is asking, but it's phrased in such a weird way, it kind of like breaks your brain. So what the way I reply is like, well, actually the questions we ask when asking about the performance of Sound ID is how precise is Sound ID and what is the recall rate of Sound ID? I'm going to dig into precision and recall over the next few slides. But as an example, let's focus on some examples from our test set, right? We're a few slides back, I mentioned we have this important split between training and testing, right? So now we're in the exam phase of quizzing Merlin, whether it learned something. So this is all audio examples that the system has never seen. And we're going to ask it which of these examples contain Northern Cardinal. Now, because we're the teacher, we have the answers, right? And so we know that these 20 examples, they do contain a Northern Cardinal. And these 20 examples, we know that they do not contain Northern Cardinals, right? So we can ask Merlin, all right, Merlin, listen to this audio and tell us, which ones contain Northern Cardinal. And maybe it comes back and it says, these 9 do as well as these 3. So what we want to ask is, what fraction of audio clips predicted to contain a Northern Cardinal actually have a Northern Cardinal localization, right? So this is a question that the teacher is going to ask of Merlin. So what fraction of these clips that it predicted to contain Northern Cardinal actually have them? Well, these are the clips that actually have it, right? We know that, and these clips do not. And so we're going to compute the fraction, right? So this is green, the number of green boxes divided by green plus red. And in this case, we get this precision value, which is going to be a number between 0 and 1, right? So 1 is perfect precision. 0 is you failed at everything. You didn't get anything correct. And in this case, Merlin would have a precision of 0.75 or 75%. Now, this metric by itself can be gained, right? It is not difficult to build a system that would output exactly 1 Northern Cardinal prediction on an example that really likely has a Northern Cardinal, right? So we can make Merlin output exactly 1 answer, And given our precision, the algorithm to compute precision, which was green divided by green plus red, this system would have a precision of 100%. This would be a perfect system. I could go out and exclaim that Merlin it has perfect precision. The problem is that Merlin missed all of these other northern cardinal vocalizations, right? So precision by itself doesn't capture the full story. And so the other question that we want to ask is what fraction of the northern cardinal vocalizations are actually detected, right? And so we can come back to our model predictions. And now we kind of just want to focus on this side over here. We're like, how many of these examples did Merlin really get, right? And so this is recall. And to compute recall, you take the total number of green examples and you divide it by green plus orange, right? In this case, you get 45. So 9 divided by 20, it was 0.45. And so we have a 45% recall in this situation. Now, just like precision, recall goes from 0 to 1. So we want a system with a recall of 1. And it's not difficult to build a system that has a recall of 1, right? You can game this metric. You do that by just having Merlin output northern cardinal for everything, right? We're just going to say every piece of audio has a northern cardinal vocalizing. And given our algorithm, the equation for computing recall, that's green divided by green plus orange. Everything's green here, right? We said everything contains northern cardinal. So this is going to have a recall of 1, right? But again, just like precision, this doesn't capture the whole story because you've said, this same system said that all of these other ones also contain northern cardinal, and of course they don't. So what we do when we look at the performance of Merlin on a particular species is we take its predictions on the test set, in this exam setting, and we look at both precision and recall. And we want both metrics to go towards 1, right? And often what you find is that these things are at odds with each other, right? So if you find a way to improve precision, you often hurt your recall, right? Or if you find a way to improve your recall, you often hurt precision. And so it's a big undertaking to actually improve both metrics at the same time, but that's what we're after. Now, we can compute precision and recall for all species in the model, and we can look at a scatter of their values. And what we're looking for is species in this green quadrant up here, right? So for Merlin, we like to see species with a precision greater than 0.9 and a recall greater than 0.7. For our purposes, for the mobile application of Sound ID, those are species that are doing well. Sure, there's more room for improvement, but those species, in terms of like grouping kind of species by performance, those ones are doing well. Now, species that are in this red quadrant, these are ones that need to be improved, right? We haven't hit a precision of 0.9 and we haven't hit a recall of 0.7, right? We need to do work to improve those species. Merlin hasn't quite learned those to the proficiency that we'd like to see it. Okay, so how do you improve a species? Well, you kind of have 2 options. One option is to iterate on the data itself, right? We can engage with our citizen scientists and we can ask them to collect more audio. Maybe the audio in the Macaulay library is just not comprehensive enough. We need more examples of a species repertoire or more examples of the habitat that species exists in order to kind of show those examples to Merlin in order to get it to learn better. We could do more annotations, right? Like, so for yellow rump warbler, we had 3,000 audio files. Right? We could just go sample more audio files and do more annotations on what we have in the library right now. We can also do annotation review. This process, experts are not always perfect, and sometimes they make mistakes. So we could go back and we can kind of review the annotations that the experts have done and see if we can improve the data sets that way. Option 2 is all about machine learning research and development, right? And so for this talk, I'm not really going to dive into here, but this is like, keeping up with the latest advancements in AI and machine learning, taking those best practices and bringing them into the project, running a bunch of experiments to figure out what the correct hyperparameters are for the model, what the correct architectures are, et cetera. Yeah, so these are kind of our, both of these kind of levers have different risk factors and cost factors. And, we just kind of take these various things into account And we do both, each week, so to speak. So we're going to definitely iterate on the data, and then we'll definitely kind of keep up with the AI and ML fields. But we can get a quick look at this annotation review process, right? So every time we train Merlin, we will also produce a report. This is kind of like actually, this is like literally like a graded exam, so to speak, that we produce during each training round of Merlin. And we'll go through and we'll go find those situations where Merlin is predicting yellow rump warbler, but an expert didn't label any yellow rump warblers in that particular section of audio, right? And so, here we're seeing, like, in this particular asset, so each row here is an audio file. We can see that Merlin is predicting yellow rump warbler in quite a few different timestamps in this audio file. So an annotator, an expert annotator, can go to this file, and this is this gray catbird recording. And they get the feedback that the model predicts yellow rump warbler in this with this kind of icon down below. But they can go back and they can listen to this audio and see, is there really a yellow rump warbler? Now, if you remember to our training example, the yellow rump warbler had this kind of strong chip note vocalization, and I kind of see these here. And so most likely the expert just kind of forgot to annotate the yellow rump warbler, or they got distracted with something else. They didn't quite finish this file. But in this way, they can kind of come back through and help us add in those annotations. That will then help us. We can then take those kind of new annotations, reteach Merlin, redo this analysis, and we'll kind of complete these cycles kind of over and over and over. And so that's one of the things I really wanted to emphasize, is this is not a linear process. This is just kind of this constant iterative thing where we're figuring out how to optimize, what data we're collecting and how we collect it, which audio files get annotated, how do we improve our teaching mechanisms to get Merlin to really learn this stuff? And then how do we improve our evaluation procedures so that we really understand where Merlin is making mistakes, where is it doing well, where does it need more help? And we'll just keep cycling through this stuff. So this process started 3 years ago, and we launched our first public model in the summer of 21, and that included just 458 species, focused primarily in the United States and Canada. We followed that up with a spring update to the public in 2022, and that brought in a bunch of species from Europe, and that brought us up to 685 species. So these were kind of like the common species in Europe. We did another fall release in 22, and there we just started doing kind of stuff in the India and Central America, while kind of finishing up some stuff in Canada or in Europe. And then just this year, we had an update in February that again kind of strengthens our India representation and our neotropics representation. Now, there's so much diversity, right, in these parts of the world that we're still kind of in this low species coverage. This model that we're releasing here in, actually, I think it's rolling out today, to be honest, adds another sort of 200 some odd species. And again, it kind of continues to increase our coverage of India and the neotropics. And this is this iterative process. We'll just continue to do this until we slowly cover more and more of the species around the world. And the Sound ID has had this huge impact on the Merlin Bird ID app, right? So Sound ID is packaged into Merlin Bird ID. Merlin Bird ID has been a great app for birders for many years. So it first came out in 2013, and it's kind of had this nice steady growth. But come Sound ID, we've seen this huge increase in users. Just this year alone, we've had 8 million active users kind of coming back to the app and using it, on their daily walks or out in the park or just in their backyards. We've had 15 million total downloads of the app, and these kind of numbers, for an academic research lab, like these are truly kind of impressive numbers. And it kind of it's going to change the way that we collect data from citizen scientists to do things like bird population monitoring, bird survey monitoring, all this kind of cool stuff that we can do through letting folks collect audio and then having automated systems to analyze it. And Eliot is going to take it from here and kind of show, what are our first tentative steps in this direction, and kind of what does the future hold. So let me switch screen share over to Eliot.
You are screen sharing. You have started screen share.
All right. Well, thanks so much for setting me up, Grant. If you came in late, my name's Eliot Miller, and I'm a Schmidt Futures postdoctoral fellow based at the Cornell Lab of Ornithology. So let me get this going, right? So I don't have time to list everyone involved in this project, not least of all because, as Grant just explained, it relies on contributions from literally hundreds of thousands of citizen scientists. But I wanted to at least, flash up a few photos of some key collaborators. That includes Daniel Fink, Carla Gomes, and of course, Grant. So the rest of these awesome folks are people you can find here on Cornell campus writ large, both here at the lab and on main campus. So I'm going to pick it up where Grant left off. Grant did a really good job of making it clear that our primary goal has really been making a high-performing app that runs efficiently on mobile devices. And there's a couple of reasons for this. First, this is a particularly challenging use case. So if we achieve success here, it's likely we can be successful in other scenarios. But also, if we step back, we can frame this development of Merlin in the context of the broader lab mission. So our mission at the lab is to interpret and conserve the Earth's biological diversity through research, education, and citizen science focused on birds and nature. So with millions of users using the app to interact with birds regularly, like Grant just said, Merlin's really knocking the interpretation and education aspects of this mission out of the park. But at the moment, it's not directly targeting other aspects of the mission, namely conservation, research, or citizen science. So I'll just insert a brief caveat here that all these people outside listening to birds every day probably does have some important indirect conservation benefits. But the point remains, can we leverage Merlin Sound ID to further other important aspects of the mission, like research and conservation? Why would we want to do that? Well, these days, as Grant just said, we've got about 27 people using Merlin to every eBird user. If we could collect data via Merlin, we could collect data at much broader spatial scales and temporal scales potentially. So this might let us add species to the set of those whose populations we model, or it might potentially allow us to extend sort of the coverage of those species. And I'll show you what I mean in a second. I also want to emphasize before I do that I'm not talking about replacing humans here. The idea is simply to increase the scale of data we have to monitor birds. Many of these species are declining precipitously, and so having more information to provide insight into those declines could be really useful. It'd also be beneficial for a variety of other reasons, not least of all because millions of more people could potentially become involved in citizen science. So it'll be helpful at this point if I give a bit more background on what the lab is doing now to directly support research and conservation. I'm going to highlight eBird here, which is a large citizen science project we've been running since 2002. eBird provides birdwatchers globally with a platform to record what they see. They report when and where they birded, how long they searched for, and critically both what they did and did not see. This then allows us to make inferences on species presence and their absence. This gives a map of where observations have been submitted from globally. The data set is really expansive at this point, but it certainly has limitations as well. Large portions of the globe you can see are essentially uncovered, but where we have sufficient data, which at this point is now a lot of the Western Hemisphere, Western Palearctic, India, Australia, New Zealand, Taiwan, we can use it to model the status and trends of the world's bird species that live in those regions. So these products that we're creating now are now finding their way into federal conservation decisions in a wide variety of research projects. I'm not going to get into the methods of these distribution models today. Instead, I'm going to treat this as a black box that takes in eBird records and important explanatory variables like habitat, climate, human disturbance levels, and then it outputs maps of abundance over time and space. So here I'm showing you two examples for the white-throated sparrow. Up here we have a sort of a distribution abundance map, and it captures time as well. So here's the non-breeding season, where it is during migration, and then the wintering season. The strength of the intensity of the pixel gives some indication of how many birds are in each spot. And then down here, we have a trends map. And so in this case, it's predicted for the wintering range of that bird. And the size of the dot tells you how many birds are wintering in that region on average. And the color tells you sort of what that local population is doing over the last 13 years in this case. And unfortunately, what we see a lot these days is big maps full of red dots. So that's worrisome. And having more data to help us, demonstrate these things better would be great. So that's what's happening now. But to return to my question before, can we leverage Merlin Sound ID for research and conservation? Today, I'll show you a bit of our preliminary efforts to address this question. Step one of this was just figuring out how to go from the continuous occurrence probability that Merlin outputs when running live over the phone to a format that's conducive to distribution modeling. I'm going to gloss over the details here, but the general gist is that by listening across longer sound files and being conservative in when we make a prediction, we're able to achieve even higher levels of performance than the live use case. I'll just refer to this as sort of the threshold method going forward, the file level threshold method. And this figure shows the results of these new thresholds. So here each dot in this figure is a species, and its position along the horizontal axis is a function of the clip level performance, sort of the live on the phone performance, and its position on the y-axis is a function of the file level threshold performance. And you can see that most dots are above this one-to-one line. So the take-home message is that if at the end of a file, all we really want is a list of what species were present, then we can do that with a really good deal of accuracy without sort of sacrificing precision. So in boosting recall without sacrificing precision, essentially. So as a reminder, the long-term vision here is integrating these acoustic predictions with eBird detections. But before we can do that, we need to experiment with distribution modeling with acoustic data alone. So for example, what sorts of explanatory variables do we want to add? Do we need to know what type of phone the user was recording with, what type of microphone they had, how much background noise? So experiments to that effect. And then critically, how do the models compare to those derived from eBird? So to get at these questions, we created a data set as follows. First, we identified all eBird checklists from the Northeast US that were submitted along with an audio recording. As Grant already showed nicely, when you submit a recording, a checklist rather, you can attach photos or audio to it. So here's one list that we did a couple of years back. Nominally, these files are going to be of the species, that they're targeted for. So in this case, it was blue-headed vireo. I uploaded a recording, but you can see here these sort of vertical. It's probably, I don't know, maybe Carolina wren. Can't remember off the top of my head. But there's tons of birds in the background of these files. And so that's exactly what we leveraged. We ran Merlin across these 40,000 matching sound files from these complete eBird checklists. We applied those file level thresholds, and we created these acoustic checklists, which we then paired with their corresponding eBird lists. Show you what that looks like here. So here you've got the eBird checklist, audio file. We run Merlin across that audio file, and we generate what we call an acoustic checklist. Normally, that's going to be a subset of what occurred on the eBird checklist, but not always. Sometimes species can occur on the checklist, on the acoustic checklist, that were not detected on the eBird list. These can either be false positives, where Merlin went wrong, or they can be cases where the eBirder, failed to detect that species. And so keep this point in mind, because I'm going to circle back to that shortly. A few brief stats here on the data set we created. It comes from around 40,000 complete eBird checklists, which corresponds to around 58,000 observation hours. The recordings attached to these lists, however, only represent 457 recording hours. So while the data set is paired, the eBirders were out detecting birds for an order of magnitude more time than we have acoustic data for. And so that makes sense. If you're out for an hour walk and you've got your phone or a microphone with you to record birds, you're not probably at least going to have it running the entire time you're out birding. So again, it's going to just be a subset. But aside from that, we've got these paired data sets now, which allows us to do a lot of fun things that I'll show you. So we take those paired data sets, we send them off to our black box. And the question is, what comes out the other side? Does it produce decent distribution estimates? So here I'm going to show you paired distribution models for one of the more vocal species in the region during the summer breeding season. Those of you who know your birds know that red-eyed vireo is, it's borderline obnoxious. It's so loud throughout the summer, just singing in the background of every sound file pretty much. And so unsurprisingly, we do a pretty good job at creating a similar distribution model to what we created using a tried and true eBird approach. So to walk you through these, on the left, we have a distribution map, predicted distribution map for red-eyed vireo in the summer based on the eBird detections, those 40,000 eBird checklists. And on the right, we have the corresponding predicted distribution based on what Merlin thought it heard in those matched audio files. Again, brighter yellow colors equate to like a higher probability of presence in the region. So yeah, pretty solid comparison there. That's exciting. Now for another interesting challenge. Here we targeted a species that it's really actually quite easy to confuse with the similar downy woodpecker. This is the hairy woodpecker. So lots of beginning birders get this identification wrong, particularly visually, but actually acoustically, they're quite different. And so we were hopeful that that Merlin actually might produce a better distribution map than eBird in this case. The question though is really like, does it? We don't actually have a good way to test whether it does. So, it definitely looks sharper. That's interesting. Honestly, having dug into the data for hairy woodpecker a little better, I'd say I'm not sure that this Merlin map is any better. But the question is, we've actually kind of reached this point where we need to figure out how to properly evaluate and validate these two different, almost competing distribution models. I'll show you another case, a good example before I move on. This is red crossbill. It's pretty rare in the study area. It might be the most acoustically well-documented species in the Macaulay Library, but a lot of those are going to be coming from out west where it's more common. In the east, it's not very common, but it is quite detectable by sound. And it's not that rare in the core of its distribution in the Adirondacks and the Appalachians. And so, yeah, we do a pretty good job of modeling this one's distribution as well. But now for a failure case. Here again, you see the eBird and Merlin maps side by side for the red-shouldered hawk. What happened here? Well, first of all, red-shouldered hawk's a pretty rare bird to pick up in the background of a recording. But secondly, blue jays love to mimic hawks in general, and particularly red-shouldered hawks. And so the result is we've got, eBirders out there with phones, with recorders, who can't believe that this blue jay is imitating a hawk, and they record it. They attach that recording to their Macaulay checklist. That's great. Thank you so much. We love these recordings. But when we run Merlin over them, it thinks they're hawks, not blue jays. And so with this sort of limited and messy data, we're unable to model this species distribution very well. We've actually tried this exercise over about 150 or so species. We find that overall we do quite well at sort of replicating a similar distribution map to that which we would, derive from eBird. But our performance really drops off for rare species, particularly the hawks that are frequently imitated by blue jays. Quick moment to just point out, we don't think this is an unsolvable problem. When we were annotating recordings for Sound ID, or when we continue to do so, we've made this design decision to not try to teach the model about mimicry. It seems possible that the model can actually learn how to tell these calls apart if we supply it with sufficient training data. So I'm hoping that we can try some examples soon to see if that's true. I'll show you some cherry-picked examples here. This is red-shouldered hawk. And this is a blue jay imitating it. I'll run it through one more time for you. Red-shouldered hawk. And the blue jay. So, those signals potentially seem separable to me. So I'm optimistic that if we send it the right kind of training data, we can solve this problem. Okay, so with what little time left, I want to show you an exciting offshoot of the project. Here, rather than simply looking to see how we might be able to integrate Merlin detections into this great pool of citizen science data, we're exploring ways to leverage Merlin to improve the model beyond their current, to improve the species distribution models beyond their current performance. So I'm going to let you into one small insight of the black box, which is that one of the things that we do account for is a measure of observer skill level. Not all birds at a site are always detectable, and this variation in detectability really scales with observer skill level. And yeah, the black box in the distribution models does already account for that, but it's in an indirect way by actually estimating observer skill level. Here with a new detection method, which is Merlin Sound ID, we can now sort of gain direct insight into how frequently eBirders are missing species. So this is a complicated graph, and I'll walk you through it slowly. We've got observer skill level on the x-axis here, with experts over on this side and beginners on this side. And what I'm showing you is the probability that somebody misses a bird that Merlin thinks it hears a bird in the background that was not on their eBird checklist as a function of observer skill level. So for experts, that almost never happens, right? There's very few times where Merlin thinks it hears something that an eBirder did not hear, if they're an expert. But as we sort of run across this gradient towards more and more beginning birders, we find that that probability that Merlin thinks it's hearing a bird in the background is rising well over 75%. And if we dig into the species that people are missing, what we find is that they tend to be common, or species that sing at like a high frequency, or perhaps they're just birds that are generally really hard to detect by sight. And so beginning birders are missing them. In other words, people are probably forgetting to record some of the most common birds. And by record, I mean report on their eBird checklist, or maybe they don't hear these high frequencies because of hearing loss, with aging, or maybe they just don't know what these birds are that are so hard to see, but sing all the time from the canopy. And so with results like these, we can more directly model the probability of these false negatives in our distribution models. As we continue the research, we think it's likely that eventually we'll be able to learn which detection methods are most reliable for which species and weigh those predictions accordingly. Just kind of cut myself off here because this pretty quickly gets technical, but I wanted to show this slide to transition to my final points. First, I want to briefly mention autonomous bird monitoring. There's places on the ground where, fortunately, very few people live. Some of these places, for example, the Amazon, are also densely packed with a bewildering variety of bird species. Many of these are extremely challenging to identify by any means. And the simple truth is that monitoring these areas is really hard. Fortunately, autonomous recording units exist that are capable of recording birds for long stretches of time. And so with enough training data and expert annotation, ultimately, we should be able to get Merlin up to a sufficient level of performance that it can be used to accurately monitor birds, even in these places where bird watchers with cell phones aren't regularly traveling. So what does the future of bird monitoring look like? Well, we've had around 900,000 people to date use eBird over the last 2 decades or so. As Grant showed, over 1 million a weekend are using Merlin now. Data integration is really the future. This doesn't just mean acoustic data, but GPS trackers like on the Falcon here, radar data that can be used to tell us when and where birds are migrating. It means more people outdoors looking for birds, both with their own eyes and monitoring devices like phones armed with Merlin. And acoustic monitoring is going to enable us to track birds in regions with few people and regions where few people are able to identify all the species that exist there. So thanks, and I'm going to turn it back over to Grant, actually.
Yeah. So like Eliot mentioned, I mean, this project is built on a ton of people. So it's really a team effort. We've got domain experts that are contributing audio or annotation. We have machine learning R&D. We have the annotators that are doing all of those boxing, and then we have a group of engineers and developers that are making these tools accessible. So it's really a team effort. So while Eliot and I got to sit up here and talk for an hour about it, there's a group of us that are working on this. And this is just a few of those folks at Cornell that are kind of part of this core team. And then, but there's this huge pile of annotators. I think yesterday the stats were like 223 some odd people that have put in countless hours to make this possible. So big thanks to these guys, and thank you to everyone that has watched. Hope you enjoyed.
Great. Thank you so much, Grant and Eliot. That was absolutely fascinating. And as someone that uses Merlin Sound ID and totally takes it for granted, I now understand just how much huge effort goes into training and testing those models. So we'll open it up for questions. We're a little over time, but we can kind of eat into the networking part of the session. While I wait for questions to come in, maybe I can ask one myself. So in my program, we work with partners around the world, and we're always painfully aware of the paradox where we have great data in places where I live, like in Nova Scotia, and Merlin Sound ID performs extremely well where I live, and yet the megadiverse parts of the planet, kind of like that slide you showed, are where we have the least amount of data. So there was some discussion that Eliot profiled around using autonomous bird monitoring and sort of joining that up with experts. But is there any thoughts about how you might upscale the branding of Merlin Sound ID? So for instance, teaming up with partners in other countries, offering it in other languages to really get people in Colombia or India or different parts of Africa to use this, because of course just about everybody has a cell phone, and it seems like there's some great opportunities there. I think you're on mute there.
Yeah, no, absolutely. I think kind of sky's the limit on this one. So the Merlin team, so a few things, like Merlin is available in a few different languages already. So Spanish is well covered. Eliot, like, correct me on if I say anything wrong. I believe Portuguese is also incorporated, and we have kind of a whole catalog of other languages. The whole app itself has already been translated to do exactly what you said, right? Make it more accessible to folks in these other regions. And then Cornell, the Lab of Ornithology as an organization, spends a lot of time on outreach, right? So engaging with stakeholders in these locations, whether they're bird clubs or scientists at other universities, to kind of figure out what are their needs and how can Merlin and the eBird enterprise more broadly kind of help them achieve their goals. So yeah, no, I think it's just kind of time. It's just like it's happening, and I think we all wish it was happening a bit faster. But yeah, we've got the ball rolling, and we'll just kind of keep pushing it.
Great, thank you. Another question. You mentioned the yellow-rumped warbler, and I live in Nova Scotia now, but I used to live up in the north of Canada and the Yukon, and of course there's yellow-rumped warblers. The North America's polluted with them, if you want to call it that. Or I kind of liked Eliot's comment about the red-eyed vireo being borderline obnoxious. But of course, they have huge variations in song and calls. Like, so the dialects are really incredibly different, at least to my ear. How much does that variation affect the thresholds that you're trying to get? So I recall a graph that said you're trying to get into that top right corner, 0.9 precision, and I think 0.7 recall. Does the sort of threshold of audio recordings and testing and training vary wildly depending on the species and its own inherent variation?
Yes. I wish that there was like one size fits all solution to this, but it's really a case by case basis. So for the yellow rump warbler specifically, we have over 200 training recordings to teach it, basically to cover all those situations you just mentioned, right? Its repertoire changes throughout its range. And so we can't just get away with a handful of recordings and hope to kind of magically work well everywhere. So for that species, we've already kind of boosted its training data set that it gets to learn from. And then our evaluation data set has increased. It has 50 recordings taken throughout its range to kind of really detail, like, which parts are we doing well in, which parts do we need more annotations for. And it kind of gives us that insight on how to prioritize getting better performance for that species. So that 100 number that I kept mentioning is really kind of more of this like minimal threshold for us to like start having the data to have this conversation. And then for each bird, we kind of like look into it and see like, oh, maybe the bird has really stereotyped vocalizations and actually 100 recordings with plenty to get decent performance. Other species may have, like you said, huge ranges, right? And so like you're bound to get some diversity in the vocalization across the range. And so there we need to sample more and more recordings across that range in order to get the performance we want, because we want high performance in North America, high performance in South America, kind of high performance across the world. And so it's just having that toolkit available to even have that conversation. That's kind of like what's primarily been the success of this project, is we have the tools that allow us to figure out what's working well, what's not working well, and then prioritize our efforts accordingly.
Great. Thank you. Okay, so a question that's come in from Alberto. I'll read off. So thanks for the great talks. I was wondering whether there are significant differences between Merlin Sound ID versus BirdNet, since they're both developed at Cornell. Which one would be better to implement a passive acoustic monitoring system in a remote region?
Yeah, it's a great question. So yeah, BirdNet preceded Merlin. So yeah, this was like the question mentioned. This was another research project at Cornell, and it's still ongoing. Um, and so Merlin got to learn kind of all the lessons of BirdNet and then improve upon it. So the performance for the species that both systems cover, performance in Merlin is going to be better because of the way that we collect the data and annotate the vocalizations and the way and kind of the insights into the benchmarking process. So the thing that BirdNet still allows folks to do is that they have a huge repertoire of birds in that model today. So the last time I checked, that their models had over 3,000 bird species. May or may not performing up to the requirements that a scientist needs to do passive acoustic monitoring, but a scientist could certainly try using that model and see if it fits their needs. And in the meantime, the Merlin Sound ID project will keep kind of trucking along, and eventually, we'll cover all those 3,000 species as well, plus more. So yeah, no, it's kind of like two tools. One, the BirdNet team is still very much focused on researchers. These are maybe perhaps focused on postdocs and PhD students that are trying to analyze acoustic, these autonomous recording unit files on their local computers. Merlin from the ground up has been designed to tackle arguably a much more difficult problem. So this is running in real time on cell phones across the entire world, right? So we have no control over the microphones. We have no control over the recording situations. The model has to be far more robust than what kind of the BirdNet folks had originally designed their system to be, right? It's kind of not fair to actually compare BirdNet because of that. So yeah, two great projects. They'll both continue to kind of innovate and help out, and eventually we'll probably see some convergence as the two data sets become more and more similar.
Great. Okay. Another question that comes to mind. You guys clearly like challenges, and you're you're really stretching and pushing Merlin Sound ID forward. And of course, this is all around filling in the gaps around presence, absence, and species distribution models. But what about, and maybe this is totally nutty, but what about abundance? Is there any thought around whether, I think about when I was younger, you don't want to let me do a point count or breeding bird survey now, but I used to do point counts, and you get multiple yellow-rumped warblers and Swainson's thrush and all that singing at the same time, and by doing a point count you could get an estimate of abundance. Do you think we can push the models to start to infer abundance as you go forward?
I can launch in for a sec on the data integration side. If we're talking about the models being the sort of polished status and trends eBird distribution models, then those are created currently with a sort of hurdle model situation where first you model the probability of occurrence and then the abundance part happens afterwards. So there's reason to think that if we can figure out the data integration part, first round, we'd just be using the Merlin detections to help with that first stage of the hurdle model. And then the abundance could be informed later by eBird data. But there's also the thought of using Sound ID to actually sort of try to make some estimate of abundance. So cool. I've got some ideas there, but yeah, Grant, if you want to say anything, feel free.
Yeah, I think like tons of open research questions, which makes it exciting. Lots of, could you, just to throw out like kind of to one up your nutty question is like, could you detect individuals, right? Like, are individuals' vocalizations unique enough that in a given audio file you could be like, this is Sally, this is Mary, this is Tom. Who knows? Got to get the data collected, be able to run the detailed experiments, but yeah, fun. Definitely just fun open questions.
Yeah, no, it's absolutely incredible. And the other thing you should probably note as a biologist, if Merlin Sound ID existed when I was back in the day, you would have been able to save hundreds, thousands of hours of sleep, because I used to have to get up at 3 a.m. to do those point counts. Another question that came in from KB Miller: is there a specific effort to link the data to help threatened species?
Yeah, sorry, just hopping in. No, in short, I know Grant's had a few sort of experiments he's been trying with pigeons in various places. If I tee up for anything there, but yeah, in short, no, but it's something that we're really excited about. There's this unfortunate trade-off, right, between data quantity and threat status. So I would say one sort of medium-term priority of Sound ID for us would be figuring out how to sort of extend the model to species with less data without losing performance, so that we can target those threatened species more directly.
Yeah, no, it's a great response. I mean, maybe possibly like another plug for a BirdNet style approach, right? Where you're going to have an active scientist really engaged in reviewing those files, and so you can get away with a possibly less performant system. Yeah, like Eliot mentioned, I mean, it's such a tough thing of like, we really want data in order to like kind of answer these questions on current performance levels, and a lot of these species that are under various stress situations often just don't have that data. So we're getting there. We're learning lessons. I guess maybe like the bright side is like we're currently learning lessons on like how we can get away with less data, right? So with these bird species that have plenty of data, give us the opportunity to run what we call lesion experiments, where we synthesize situations where it's like, okay, what if we only had 10 audio files for a bird? How does that compare to a data set where we had 100 or 1,000 audio files? And it kind of allows us to really understand what is the big trade-off? What are we really losing when we go to those situations where we're in a low data regime? Yeah, and again, kind of like lots of open questions and lots of cool research to be done.
Wow. Okay, maybe final question, then we'll wrap this up. But thinking about taxa that vocalize, obviously birds are the most famous. And if you can solve this for birds, which you are, this should be pretty easy for other taxa. And I'm thinking about amphibians in particular, but there must be, are you getting approached or are you helping others to sort of apply this AI approach to detect other taxonomic group species?
Yeah, so we've had a pretty like tunnel vision focus on birds. I think the lessons that we've learned could be applied to the other taxa, whether they're terrestrial or marine. We haven't taken a lot of those steps yet. So we are collecting data in the Merlin annotation process for amphibians and mammals as they show up in the files. So we are kind of slowly growing a data set there because at least in the United States, tree frogs and other things are kind of common confusers for people. And so we would like to be able to point out that, oh, what you're hearing is actually a frog. It's not a bird. But I think overall, I think you're right. Like, I think the lessons that we're learning here can be applied to these other taxa. The big missing piece, and maybe it's not missing, it's not necessarily at Cornell right now, is this community of experts that can come in and help you work with that data, right? Like Eliot mentioned, there is no replacing humans in these pipelines. It's just kind of like shifting priorities. And like for birds, what we need are folks who can listen to audio, tell us what's vocalizing, and draw those boxes. I imagine we would need something similar for amphibians and mammals and insects as well. And so it's building up that community and having, which takes a while, unfortunately, but yeah, having that community of experts that can really help come in and participate in the process.
Great. Thank you so much to both of you. We should probably wrap this up now, but absolutely fascinating talk. And honestly, it's incredibly exciting. And if anybody that's listening in doesn't have the Merlin Sound ID app on your cell phone, shame on you. You need to get it. It's absolutely incredible. I have a diverse set of friends that are not scientific, not even really interested in nature, I thought, and they are avid users of this app. It just opens up a whole other world for you. So thanks again to both of you, Eliot and Grant. Such an interesting talk, and keep up the great work. So we won't have much time on the neural network, but for those that want to join, if they have any other questions or network with Grant and Eliot, just please join there. So thank you again.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.